welcome back. Today is the fifth class in this sixth class series on semiconductor devices. And as we discussed in the last class, we were in the middle of talking about field effect transistors. In particular, essentially we had come up with essentially a complete model pretty much of how to understand a field effect transistor, but we didn't put all of them together. That we left for today, and that's where we will start. And before we get going, I think there were a couple of questions regarding things like, one of the questions was, somebody asked me about problems for practice. Somebody asked you? Yeah, great. So I will, I hope all of you have access to this box site now. If you don't, please email Amit, and he will give you access to this box site where some of the slides that we use, I've been using slides somewhat sparingly, not too much, but the slides that are used that has a lot more than what we are covering in this very short course are posted there. There's a little Mathematica file which has a few tools that we have used for illustrating things in the class is also posted, and you can run it on your own and play with it, change it to your needs. And the lecture videos are also posted. And what I'll do is I will post a set of problems that you can practice. And the other thing is there are lots of books. If you want, I can direct you to some books that have nice problem sets at the ends of chapters that you could also practice. So, okay, let's finish the discussion on our models of field effect transistors, or FETs. And just to be clear again, what we have developed for the FET model is what I would call really the most modern understanding of very small transistors in the limit of when there is basically no scattering at all in the channel. And this is a relatively new model. There are a lot more. If you pick up most semiconductor textbooks, they actually haven't yet, many of them haven't yet incorporated this sort of picture, which is to an extent a full-blown quantum picture of transistors. And this is the paper I had mentioned in the last class, which we are following. It has a little bit more detail in the class. What we did in the last class, just to remind ourselves, is we're looking at a field effect transistor. The way we have constructed it is we started with a semiconductor, which is actually we assumed a two-dimensional semiconductor, a sheet of semiconductor. Here, this particular paper does a more conventional semiconductor, which is a silicon MOSFET. But what I want to assure you is really there's no difference between what we're doing and what they do. In fact, because of the fact that it is a 3D semiconductor in which you create an inversion channel using the gate, there are a lot of other things you have to worry about, like quantization, ground state, this, that. Here, we really, once we start with a 2D semiconductor, we don't have to worry about many of these things. It becomes a little simpler, is what I'm saying. And after we took this two-dimensional semiconductor, what we did was we had two regions which were heavily doped. We imagine these are heavily doped, and then there are contacts made to the two regions, which are source and drain. And what we have done is really we have, for example, grounded the source, and we are going to apply a certain voltage on the drain now, which we are calling V sub ds, drain with respect to the source. And this part of the channel in between, and this is kind of the important part of the transistor. What we have done here is, this would be a normal semiconductor channel, except now we have put in between the channel and another metal, which is the gate electrode. This is the gate electrode. We have put an insulator in between, right? So this is insulator or a barrier for electrons with a thickness Tb. And the dielectric constant we said was epsilon sub b. And essentially using this gate, specifically what I mean is using the voltage on the gate we are electronically controlling how many electrons are there in the semiconductor channel. That's the whole game, really. And as I was mentioning, ideally I would like to kind of complete it from on both sides, make a double gate and that sort of thing. But what we did in the last class was we were able to write down what would be the carrier density in the semiconductor, right? Let me write that down. And what were the approximations also I'll say. So for example, if both of these were grounded, meaning both the drain and the source were grounded, then you really have a two-terminal device, the gate and this, right? And that's a metal insulator semiconductor two-terminal device. And when we ask the question, what is the carrier density in the semiconductor, the sheet density, right? As a function of this voltage, if this was grounded, there's no such voltage, right? And we spent actually pretty much all of last class to find that answer, right? And this was a very important thing. The answer was very revealing. What it said was you cannot just have a linear relationship. What you have to do is solve an equation. And just to remind ourselves again, the equation looked like this: e to the power carrier sheet density over this characteristic barrier capacitance times e to the power n, again sheet density over a characteristic quantum carrier density minus 1 is e to the power VGS minus V threshold over the thermal voltage. If you remember, we derived this in the last class and said that if you want to find how much carriers are there in the channel as a function of the voltage you apply here, solve this equation. And we looked at it in various regimes. When gate voltage was much larger than the thermal voltage plus VT, we saw that carrier density, just to summarize, for VGS minus VT much larger than the thermal voltage. We saw that carrier density went approximately as the quantum capacitance times the barrier capacitance, the two in series, times the gate voltage minus VT. Right? That's what we found. This is a linear relationship with no dependence on temperature. This was the on state, in some sense, of the transistor. And the other extreme was when VGS minus VT was much less than thermal voltage. You're off. Under that situation, the carrier density changed exponentially, VGS minus VT over threshold, and that's what gave you all things like 60 millivolt per decade and that sort of thing, right? So we did that in the last class, and now we are asking that. So all this, all this is kind of true if this is also grounded, and we're just applying a gate voltage and finding the charge in the channel. So to set up the transistor problem, on the other hand, what we did was we imagined that the transistor has a length from the source edge to the drain edge. The length is L, the width is W. And we said that, well, there are electrons that are going to be injected into the channel. As you, for example, if your gate voltage was very, very low, there were not much electrons in the channel. And then when you increase the gate voltage, you are filling electrons in the channel. But we said, let's not look at the real space for a second. Let's look at the K space for electrons, right? And we found that in K space, the electron, again, I think, if you have taken any course on solid state physics or such, you would just sec. Yeah, if you have taken any courses in solid state, you realize that whenever we say things are getting quantized and all that in a large dimension, these are essentially matters of convenience, because we are going to, instead of summing over all modes, we're going to integrate over it, because they're very closely spaced, it's very dense and all that sort of picture. So, as far as what L and W you choose in the end, really, in a periodic boundary condition sort of picture, it really doesn't matter. But in a sense, what we are saying is, in K space, you have this grid of K points, which are individual modes. And now kind of very important to realize is when we apply the gate voltage, the physics of the problem says that, look, you have all these possible modes for electrons. And then if you didn't have any carriers, I mean, very low density of carriers, then let's say that's our origin, O. If you had very low density of carriers, if you're sitting deep down in the off state, pretty much all modes are pretty much empty, very low occupation function, right? And then I turn on, I crank up the gate voltage, take it above threshold, quite a bit above threshold, a few kTs above threshold. And then you see you have quite a bit of carriers now, right? Meaning 10 to the power 12 or 10 to the power 13 per centimeter square. So what you have done is essentially you've filled a lot of these modes now, right? If you don't have if you don't have a drain voltage, then you can see, first of all, how are you filling the modes, right? Remember when you apply the gate voltage, again in terms of the band diagram, gate voltage, and if you remember, this is what happened, the Fermi level you can consider of the source or the drain. When they're shorted, they're the same, right? Source and the drain are the same. And the conduction band of the semiconductor is here, and the Fermi level of the metal is here, and this is your Q times VGS. We drew this picture, and then you fill it. So what the gate battery is doing is it's taking electrons away from the metal, right, and it's injecting it into the semiconductor, right? And you can see if these two are shorted, the electrons will be injected from both sides. You see that, right? Equally, if they're shorted. I mean, there's no preference which way. So this is kind of an important picture to realize that if I were to now draw, let's use, since we have some color today, let's use color. So let's say I'm going to choose this point and try to draw an energy band diagram all the way to this point here in the semiconductor. Right? So what we drew here is along this direction, right, in the vertical direction. And then now we're going to draw in the lateral direction from the source to the drain. So drain and source. Right? And the picture this is again something we had drawn, and in fact, let me actually use the colors because it will be, this is one place where the color would be useful, so let's use it. So the energy band diagram from the source to drain at 0, source drain voltage, meaning when they're shorted, the bands look something like this. This is my conduction band edge, valence band edge, just a gap below it, and band gap. Right. And what I'm trying to really say now is, look, there are electrons that are getting injected both from the source and the drain contact. Right? So let's actually use some colors to label those electrons. From the source, let's say it's orange, and from the drain, it's whatever this color, green. Okay. The two baths of electrons, in some sense. I mean, in thermodynamics, this is a metal contact. It's in equilibrium with this source, with the source electrode here, which is grounded. So it has a certain Fermi level. Right? A metal, just like a heat bath, it has a certain Fermi level. Let's call the Fermi level of the source. Does that make sense? Similarly, this side. Wait, I already screwed up. Okay, no, colors should be right. Fermi level of the source is whatever is this metal is sitting at a Fermi level. It has a certain Fermi level, and it has a unique Fermi level, and that is it. Similarly, here you have the drain has a Fermi level of the drain, and they need not be equal, but when they're shorted, they're obviously equal. Right? Meaning there is no potential difference between them, so they're equal. And then really, this point then is. This point here is E Fermi of the source, the line there, and this line, the top here, is E Fermi of the drain. That's what we're saying. And as a result, there are electrons getting injected to the, from here, this way, into the channel, and from here this way into the channel, and there's a certain barrier height, and that barrier height is being controlled by the gate. That's the whole game, right? As the gate goes more into the on state, as the gate becomes more and more on, then this barrier height is going down, right? And you're injecting more and more carriers from both sides. And the carrier density in the channel is increasing exponentially. When it was off, it is increasing exponentially, and then once you hit on, then it slows down a little bit because you have hit a very large density of states now. Now you need to give a lot more carriers to make a little change in energy, so Fermi level. So in this picture then, if I were to draw in the K space, right, and then this is kind of a critical point to understand that, look, so there is a little, Fermi Dirac distribution, this is the Fermi level, so there is a tail of electrons that goes, something like that, right, in the band. And this tail of electrons, for example, at that gate voltage, there is a barrier here, and this much electrons are essentially going to get injected, right? So half of them are going to the right, and that sort of picture. Similarly, here you also have the tail, and again, this fraction is going to get injected. There's no barrier for them. That's the meaning of it, right? And now, if I go to the K space, you can see that if the carriers are injected from the source, and I'm going to make a very important assumption that once they're injected into the channel is either very short or you have a very high mobility, very clean material, such that there is no scattering of the electrons at all. Meaning they get injected and they move what is called ballistically, meaning if an electron is injected at this energy, for example, this electron gets injected. So it's essentially moving ballistically like a wave. It's all the way till it might end up on this side. So it might end up in the drain. Similarly, an electron getting injected from here, from the drain, is also moving ballistically. And so there's no mixing between the two. Does that make sense? I mean, an electron cannot turn around and go back to the other. That's the meaning of there's no scattering. If an electron gets injected, it keeps going in the same direction. It doesn't waver in its orientation of velocity. Yeah. Right? I mean, ballistic, that's the meaning of ballistic. It doesn't change its direction. Once it's injected, it keeps going. And that's, you can imagine there are, a lot of, the way to really imagine is, you can think there are a lot of little, at each energy there's a little source. You can think of it as a laser. That won't make you any, so the laser, as it goes, it keeps going like a wave, right? It really doesn't scatter. You can think of it that way, and that's the meaning of a ballistic transport. Or you can think of it, I think, another great example is if you have lanes, right, going to the, north, east to west and west to east, there's really no mixing between them. So they keep going at the same energy, and they don't mix. And so that's the idea of a ballistic transistor. And in that case, what you realize is in the K space, you have a very interesting picture now, right? In the K space, you will fill the modes that are going to the right, the modes that are moving to the right, have all come from the source. Does that make sense? All the electrons that were filled and they're moving to the right, what does that mean? It means the Kx is positive. Right? Kx is positive, meaning that's the electron that's moving to the right side. That's the meaning, right? Because you can think semi-classically that the velocity, actually not, quantum mechanically, if you ask me, well, here's a mode, here's one mode. What is the velocity of that mode? What direction is that electron moving in if that electron is occupying that mode in K space, right? And the answer to that is if you know what is your energy as a function of Kx, Ky, right? To find the velocity, let's say, if you know the band structure, this is the meaning of band structure, right? If you know E as a function of Kx and Ky, let's say we are talking about the conduction band, you can label it E sub C. If you're talking the valence band, label it E sub V, but you know the band structure. Then the velocity of that state is called what's called the group velocity at any Kx and Ky, right? And that is 1 over Planck's constant times the gradient in K space of this EK diagram. Now, this is a very important result from solid state or condensed matter physics. That if you know the band structure of of any material, not necessarily semiconductor, you can have a metal, you can have a topological insulator, whatever. I mean, it doesn't matter. If you know the band structure, here's the group velocity. That's kind of an interesting thing. Over the last 10 years, there's actually another term related to things like Berry curvature and all that stuff, but let's not bother about that right now. I mean, that's also pretty interesting. It has got to do with a more geometric or topological sort of component of velocity. But for our discussion, this is all we need for now. Yeah? And this looks complicated, but really what we're going to do is assume that we are dealing with parabolic band gap semiconductors, meaning that conduction band structure is the band edge plus h squared by 2 m star of conduction band times kx squared plus ky squared. So this is really we're saying it's a parabolic band structure. EK diagram is parabolic. And it's a reasonably good approximation for as long as you're at the bottom of any band, because I think you know by definition that a minimum of a function, no matter how complicated the function is, the minimum, at the minimum there is no linear term, there's only a parabolic, right? There's, by definition, right? Because the slope is 0, right? So the minimum, this is always a decent approximation. Clearly it fails if you have a linear dispersion, right? I mean, like graphene. But then what I'm assuring you is whatever we're doing, you can take the band structure of graphene, feed it in here, it'll give you the right answers in the end. I'm just saying, if you choose a parabolic band structure, we'll get what we're doing now, right? If you don't like parabolic, you can do whatever else you need. It'll work out just fine. Right? Okay, so if that is the case, if that's the band structure, so let's say this is an example is a parabolic band structure, then clearly you can see that the group velocity. So I feed it in here, and what I get out as what is the group velocity? Maybe you can tell me. If that's the band structure, what would be the group velocity? So you just feed that in, right? And what do you get? So you see, this is this is not changing in k space, conduction band minima. So only this thing, right? And it's just h square k square by 2m. It's a parabola, right? So when you take a gradient is always going to give you a vector, right? So it's a velocity is a vector. It has direction, right? So this is the group velocity. And when you take the gradient, what you get is the group velocity is h bar over m star of c times kx, and this will be oriented in the x direction in the k space if you want, so times ky, right? So that's how you just take the gradients, right? And when I write x hat, it's just it's that direction. This is direction we are labeling as x hat. You can label it whatever you want, right? So it's just a direction in that space, and that's y hat. Makes sense? That's the group velocity. It's classically it's just momentum by mass. Momentum, h bar k is the momentum, and by mass, momentum is mass times velocity, either whichever way you want to look at it, right? So, but this is also the essence of quantum mechanics. You can see that it's saying, well, you have something that has mass, okay, like an electron, right? This h bar k is the momentum. What is that? That's one of the fundamental tenets of quantum mechanics. H bar times k is the momentum of something that has mass. What relation is that? So if you remember, so let's see, h bar times k is 2 pi by wavelength, right? And h bar is h over 2 pi. So what it's saying is momentum is Planck's constant by wavelength, right? That's the de Broglie relation. That's one of the hearts of tenets of quantum mechanics. So if anything that has mass and has obviously, because when it moves it has momentum, how do you write its wavelength? I mean, it's all there. Wave mechanics is already buried in this relation. Yeah.
One question is, this is based on ballistic band diagram, right?
Yes.
If it's linear, then the velocity is a constant?
Saying if it is linear meaning band structure. Yes, band structure you mean, right?
Yes.
E versus K. Yes. If it's linear, like in graphene,
yes,
it's conical. So in graphene, an example would be, instead of this example, right? If we write that, look, what if your E kx comma ky, in graphene it looks like h bar times some characteristic velocity times kx squared plus ky squared. That's how the energy looks in graphene. It's actually a conical dispersion in 2D space. And again, plug this in, apply it here, and you will see that the velocity in graphene, interestingly, what you'll get is the magnitude is VF, right? The magnitude is VF, but the direction has, so again, if you fill this state, the direction is, radially outwards. So the magnitude is always the same. It doesn't change. But the direction looks like kx, x plus ky, y over square root of k squared plus ky squared. You can plug it in and you'll see this is what you get, right? So all it's saying is, if I have an electron at this mode, it's moving with velocity VF in that direction. This mode is moving in that direction, and so on. But all the magnitudes are the same, and the direction is different. That's what it's saying, right? In a parabolic band gap semiconductor, it is also always radially outwards. You can see it's radially outwards here. Okay? But as you go closer to the origin has no velocity. Kx is 0, ky is 0 velocity. Right? As you go out, it gets bigger and bigger. You see that? I mean, because it's proportional to kx. Momentum is proportional. The velocity is proportional to momentum. So little velocity, larger velocity, and large, and so on. Right? Does that make sense? Farther out states have more velocity, and it also is radial. If it's parabolic, it's radial, is what it says. So you can join it from here and draw. So you have all this thing. So if that's the velocity, so what does it really mean? It means that let's connect it back to the problem at hand, and we have injected carriers from the source, injected carriers from the drain, and what we are saying is the carriers are filled all the way to a certain distribution function. So the right-going carriers. Let me now kind of use a little color. So the right-going carriers, I have filled it. Maybe I'm going to draw a little half circle like that. Okay? All these modes are filled by the source. Does that make sense? I mean, all the ones I colored with this orange, all those modes are filled by the source. And how much is the filling? That whenever we say how many states are filled, you always have to look for one number, and that is what's the formula, what's the Fermi. But here you see there are two different baths. I mean, one is doing its job, the other is doing its job. They could be independent. Right now we're saying they're the same. They could be independent. And the moment you apply drain voltage, they become independent of each other, right? But right now we're saying that all these states have filled from the source, or in other words, what we are saying is all the electrons in this ballistic transistor that are moving to the right they are moving. So there's a chance where there's non-equilibrium, but they are still in equilibrium from where they started, and then that's the source. They're in equilibrium with the source contact. That's the meaning. So what does that mean? It means that the right-going states are filled according to a relation which is a Fermi-Dirac distribution, but their Fermi level is exactly equal to the Fermi level of the source. That's all it fills. The source fills it, and those carriers are in equilibrium with the source. Similarly, the left-going carriers, I think you can see now, hopefully the argument, the left-going carriers are filled by the drain, and therefore they have some characteristic Fermi level, and that is the Fermi level of the drain, the left-going carriers. And see the picture that, there are not just carriers moving purely to the right. Yes, this is moving to the right, but if you look at this one, it has a component of velocity to the right, but also a component, going in the width of the device. Meaning, there are carriers not just injected, that are moving to the right from the source, but there are carriers that are moving that way, that way, that way. You have this whole kind of semicircle of carriers that get injected. Do you see that? I mean, because it's a two-dimensional, in the metal and the contacts, it's two-dimensional, right? But it's just that when we do the sum for current, these two components will not contribute anything to the current, because they're going the wrong way. They're moving. It's not like they're not moving. They're moving, but they're not going to make it to that end, right? They're going to go back and reflect and do that. And you can actually look at those components if you apply a magnetic field. That's called Hall effect. Right? If you apply a magnetic field, then you can see those two components too, right? And then things like that. Let's not get into that aspect now. But so again, that's if you understand this picture, that left-going carriers are in equilibrium with the drain and right-going carriers are in equilibrium with the source, I think we are kind of done. The rest of it, you can work it out yourself actually, but we'll just work it out now. Any questions here? I know there are a lot of assumptions and that sort of thing, but any questions? Yeah.
This is based on the conduction band of the source and the drain, right? Not the conduction band near the gate part, right?
That's right. So that's right. So the Fermi levels are indeed the source Fermi level and the drain Fermi level.
I mean the conduction band.
So the conduction band is changing in space, right?
Because the group velocity is also, it's not related to it.
Yeah, very good point. See, yeah. So EC can change in space, right? But the group velocity doesn't care. Group velocity. It's a beautiful or rather sometimes confusing when you look at it first, because I think 2 or 3 classes ago we talked about drift diffusion model, field, this, that, right? And the field, carrier density and all that. In quantum mechanics, there is no field. This is very interesting. In quantum mechanics, you look at Schrodinger equation. There is no field. There is only potential. Right? Quantum mechanics doesn't care about diffusion, drift, and all that. The claim is once you do this, you'll get all of that. You'll get all of that. Now you judge what is what, right? And it is actually correct. If you do it quantum mechanics, you get all components, and then you judge what you call drift, what you call diffusion in the end, right? And the other thing is drift. The way we classically look at it, if you look at mobility, right? And I was going to actually, maybe when I finish this discussion, we'll come back to it. Mobility depends on E times some scattering time over effective mass, right, for example, right? This is a semi-classical picture where this is scattering time. If you make the material purer and purer, there's less scattering, meaning the time it takes for scattering is longer and longer, right? But in the limit of completely pure material where there's no scattering, you don't have a concept of mobility. That concept is wrong. So we are saying that we're going back to the roots and saying, what will happen if there's no scattering at all, right? And that's what we're answering now, right? And then I'll connect it to, hopefully with time, I'll connect it to the picture where we have the mobility and drift diffusion once we are done with the quantum picture. Because I think you realize that, everything which, the reason why, Shockley and others came up with this sort of a model, and I'm going to actually talk about it. In the beginning, in 1950s and 60s when the FET was being, understood, is they completely could not believe that a transistor with large dimensions and all that would be so quantum mechanical. I mean, they thought it must be a completely classical device, right? So they could have actually written down what Natori did in his paper, but they didn't because they had a hard time believing that this could really be quantum mechanical. It's such a long, and all that stuff, right? But once you make materials pure enough and write semiconductors and all, even at micron length, these things are close to ballistic, right? And as usual, the quantum picture is actually a little simpler, but you have to mix and match both quantum and the classical Shockley long channel sort of transistor model to understand all aspects of a transistor. I mean, anyway, so that's the connection, and I'll make the connection in the end, right? Yeah.
So an electron coming from the source, it has a specific kx and ky, and it retains that kx and ky until it reaches the drain.
Correct.
So the energy of that electron remains the same.
Yes.
So with respect to the conduction band H, the electron energy will be the same. But in an absolute scale at the gate, the electron energy changes. If you
in the gate, you mean?
Yeah, if you just superimpose the parabola on the band structure, on the band.
Yeah. So, right, like this.
Yeah, and then if you impose the parabola at the source,
then
the electron intersects the parabola at 2 different points. So
correct.
So the kx and ky, how do they remain the same?
Yeah, no, you're asking some interesting questions. No, that's right. So you're saying that, look, then clearly I can draw a parabola here, which is the band structure here, a parabola here, which is the band structure there. And the moment I look at it, for that electron at that energy, it has a certain k that looks like that. But here, it has a less kinetic energy. So it has clearly a smaller k. And all these problems are actually exactly the same as light going through one medium to another. It's exactly the same, right? So when I say there is no barrier for electrons, there is no energetic barrier, but there is a momentum mismatch barrier. And when you write the equations right, you'll see that there will be some k's, some energies that will not fit in there. They will get reflected. Even if, clearly this energy, what I'm trying to say is you can calculate the reflection coefficient across here for each of those energies, right? Once you reach equilibrium, though, the Fermi level of the right-going carriers becomes this. After all the reflections, all that has happened, it becomes this. So that's really what I'm doing. So we're saying, let's look at the steady state, right? Once you have turned on the voltage and everything is due to, but what you said is exactly correct. There is reflection, and there is refraction, Snell's law, all that stuff goes on here too. And if the effective masses are different, then you have quite a bit of reflections. If the effective masses are similar, then it looks more like the same medium but going at an angle. almost, not exactly the same, but it's very similar in many aspects of it.
How do you observe Snell's law in electron devices?
You can, Snell's law, or you can think of, for example, in classical electromagnetic theory, you have what's called a quarter wave transformer. If you have, a barrier of quarter wave, and then, you design it, and then it gets reflected, 100% transmitted, right? And that's the example of that you put, or you can have two of them, you put two barriers, you get a resonant tunneling diode. So that's exactly the same business, really no difference. So, yeah, okay. With this picture then, let me write down the carrier densities of the right-going states and the left-going states, and with this picture of velocity and all, we'll finish the story now. And what I'll do is I'll take some liberties of skipping a few equations, but I'll write them down, and I'll also post the notes, okay? So what I want to do first is, look, I already found this carrier density as a function of gate voltage. And the solution to this equation, let me just label it as carrier density as a function of VGS. That's kind of the solution. That's the in it are all situations, on state, off state, all that. This is a functional form. That's all I'm saying. Remember, log scale turn on, and then a polynomial saturation. So this is the carrier density as a function of gate voltage. Now, in K space, what is the carrier density? You look at this picture, and now you can think a lot of things geometrically, okay? So what I'm saying is, maybe you can tell me what would be the carrier density if I look at this picture now, right? It's kind of related to what? The radius or the area of this thing, right? Because if you remember the last time we wrote down some relations, and in this picture of carrier density, all we are saying is carrier density is equal to a sum of occupied states, kx comma ky, right? And over all kx, all ky, sum everything, all modes. And then we said that every mode can handle two spins, it's fermions, and then there are number of valleys. Each of them is a copy of this situation if I have multiple valleys, right? And then I divide by the area, and that is my carrier density, right? This is what we had written in the last class, right? And this is a very general relation. This is not necessarily true for. It is true for all kinds of materials, not just necessarily semiconductors, semi-metals, metals, all that stuff. And now what we're going to do is, looking at that picture, we see there is a right-going half and a left-going half. Okay? And I'm going to write it in that way. Okay? So I'm going to write the carrier density as a sum of a right-going half and a left-going half. Right? And when I do that, let me explain what I mean by that. WL, right? And all I'm doing is summing for kx greater than 0. I split it into two half circles, kx comma ky, plus, instead of writing kx greater than 0, let's just say right going. Let's just put an arrow saying it's all going to the right. And there's an arrow going to the left of f kx comma ky. But I think you will agree with me that these two f's are actually not necessarily the same. If I apply a drain voltage, they can be different. Why? Because these functions are still Fermi-Dirac distributions. But the Fermi-Dirac distribution is completely determined by the Fermi level, right? And the Fermi level for the right-going carriers is of the source, and the left-going carriers is of the drain. That's the difference. That's the only difference, actually, which means that I should write here for right-going carriers, these are in equilibrium with the source. So the Fermi level for that is the quasi-Fermi level of the source. And this is the Fermi level of the drain. So that's really the main difference. You can see we are again splitting the same thing into two, because in anticipation at the drain, when I apply drain voltage, they will become quite different. Right? So that's the reason I'm just splitting it into two. And the sum here is over all kx ky. And let me just explain, rather briefly now, how do you evaluate that? You probably have seen it. If you have done any EMAG theory or other things, you've seen sums like this very often. What we are going to say now is it's kind of a densely spaced k points, a lot of k points. The separation between them here, this one happens to be 2 pi by L, kx, and this one happens to be 2 pi over width, ky, delta kx and delta ky. This is the mode spacings. And then it's exactly analogous to mode spacings of a laser, for example, and then what we're going to do is convert the sum over kx, ky's into an integral, and let me write that down over kx's and ky's. Sum to an integral. And kx's are separated by 2 pi over L, so this is, I think you kind of know this sort of dimensionalization, 2 pi by W. And then what you have here is Fermi-Dirac distribution. I'll write the first term in its full-blown thing, and the second term I'll skip. So I'll get EC plus H square, kx squared plus ky squared over 2 times effective mass of conduction band. That's the total energy of the electron minus the Fermi level of the source. That's the first term. Right-going carriers are in equilibrium with the source. Right? Whole thing, let's write it as exponential here. Whole thing divided by kT. Right? You see, this is just the Fermi-Dirac distribution, but the first part here is the kinetic energy. The total energy, potential energy plus kinetic energy. Right? Band edge is the potential, and then the kinetic energy minus the Fermi level of the source. So that's the first term that's going to the right. And now, and then there's another term exactly like that. Well, since we had it, let's just write that down. It's just going to look a little forbidding, but really it's the same deal. 2 pi by L, 2 pi by W, exponential of conduction band edge plus the same deal, kx squared plus ky squared, effective mass of conduction band minus the Fermi level of the drain now. Okay, so that's over kT. That's your full-blown expression. And then the thing is, you notice right away a few things. Is this clear or any questions? I mean, essentially we just split it into 2. Okay? And all you have to do is, when I say right, when I'm integrating over the right-going carriers, I must only retain the right-going carriers, not the left. I shouldn't double my sum. I just have to make sure of that. That's all. Okay, so first things first. You see one of the claims I was making earlier, and you see that now that your W's and L's really will cancel. These are normalization constants, periodic bound, because they cancel out. They don't matter in the macroscopic, in that dimension, so they go away. And what you're left with is an integral that looks, let me just write it down, the summary of that is when you evaluate this whole big thing here, what you're going to get is, remember what we are calculating is the carrier density, the sheet density of carriers, okay, NS. That's what we are calculating. In fact, implicit here is NS is dependent on the gate voltage. So that's implicit. It's dependent on the gate voltage. I should be writing maybe NS as a function of VGS. That's what we're really calculating. And what you get from here is, let me write that down. After you evaluate this, how do you evaluate it? Well, you can write, you can go to, clearly, here rectangular coordinates is not good. You just use, from the symmetry of the problem, you change to a radial coordinates. Make a substitution, like kx is k cosine theta and ky is k sine theta, right? You make some substitution like that, and then dkx, dky, just that thing becomes k dk d theta. Right? That's what it becomes. Right? And then kx squared plus ky squared just becomes k squared. So it's the radial coordinates. Now when you integrate the theta, instead of going from 0 to 2 pi, you go from minus pi by 2 to plus pi by 2 for the first integral, right? And you go from pi by 2 to 3 pi by 2 for the second, right? So you just retain the right terms now. And this integral, after you do that, is maybe I'll just write it once because it's very useful. The integral looks again like this, so you can then make a substitution. You will get k dk over 1 plus e to the power H square K square by 2 times effective mass of conduction band. H square K square by 2 times effective mass. And then I'm going to pull out this and this to the right. And you see this term reappear again. What I'm going to get here is minus eta sub s. Okay? So m star kt. Okay, there's a kt here, and eta sub s. Eta sub s is EF of the source minus EC over kt. Right? And this is kind of the degeneracy factor which we have talked about so many times. Eta sub s is EF of source minus conduction band edge over kt. So you see this is kind of the distance of Fermi level from the conduction band edge. Right? So that's eta sub source. And so that's our label. We are just labeling it as eta sub s. And we don't know it yet. And we'll see that there will be an equation in the end that will tell you what that is. Okay, and this integral goes from 0 to infinity. And there's some stuff sitting in the front. And I think you know how to deal with this. You just substitute that as energy and all that. And what it becomes is an integral in, it's a Fermi-Dirac integral of 0th order. This is what you're going to get. It's a Fermi-Dirac integral of 0th order with the argument. This is the argument because k is integrated out. Once you integrate, k is gone, right? Okay, so you get a Fermi-Dirac integral of 0th order, and that has an so there's some stuff sitting in the front, but that has an exact integral, and it's just an integral of 1 over 1 plus e to the power something, and it looks like natural log of 1 plus e to the power eta s. That's really it. Natural log of 1 plus e to the power. And what is sitting in the front is the density of states d naught times kt over 2, because you only integrated over half circle. First integral will give you a half, the other will also give you a half. So let me write down the full relation then. After you solve that integral, what you'll get is d naught kt over 2 natural log of 1 plus e to the power eta sub source. What is eta sub source? It is this. Okay. And similarly, eta sub drain will be Fermi level of the drain minus EC over KT. Okay. Drain. Right? And what you'll get is plus natural log of e to the power that, but you can now see I just multiplied the two, right? Because if you remember, I claimed a lot of math in semiconductor physics happens in exponential space, and that's an example, right? So you get log of 1 plus something plus log of something else, you get a product, and you see very interestingly that if the source and the drain have the same Fermi level, you get log of 1 plus this whole square, right? Only if you have the source and drain at the same Fermi level. If you don't, then you don't get the square, right? But if you get the square, then the 2 will cancel this. You get density of states times kt and natural log of 1 plus that, and that is really the carrier density in 2D systems, normal 2D systems. Right? What is d naught? I think we have written that is spin degeneracy, valley degeneracy, effective mass over 2 pi h bar squared. That's d naught. So all that stuff gets just clubbed into the front, right? And density of states in 2 dimensions, always as units of 1 over 1 over energy. Density of states is how many states per unit energy. So there's energy, and in 2 dimensions, it's in area, or centimeter square. And so this is 1 over energy centimeter square is d naught. Kt is energy, so you get 1 over centimeter square. That's the sheet density of carriers. Actually, let me. Yeah. Okay, so. That's our sheet density actually as a function of gate voltage. And that's a very important relation for this MOSFET, for the ballistic FET. We don't know yet what is eta source and eta drain, but that's the relation. Now, when we apply a drain voltage, right? So now I'm going to apply a drain voltage and make the band diagram. Let me just sketch it now. So the band diagram now, when I apply a drain voltage, is going to, the Fermi level. What does it mean I'm going to apply a drain voltage? It means that the source, the Fermi level of the drain is not going to remain same as Fermi level of the source. That's all. Right? So and how much will be the difference? Let's say I apply a positive drain voltage, then I'm going to actually push it down. Now the way to look at it intuitively is you're taking electrons away, in some sense. So you're going to push it down, and so let's say the Fermi level of the drain goes here. So this is Q times V drain source voltage. You move the Fermi level of the source down here, and when the Fermi level of the source has moved down here, this region is still heavily doped n-type. This cannot. It has to remain charge neutral. It cannot just lose electrons. So what will happen is the bands have to bend, and let me sketch it now. Okay, so the bands now have to bend down, and then go down gracefully till here. Okay. So the band that was here has to bend like that. Okay. If the conduction band bends like that, the valence band has to just follow. The band gap is not changing just because you applied a drain voltage. The band gap just follows. So valence band also bends. And now you can even classically see that an electron would like to kind of move this way, right? Again, from our earlier pictures, it's going from the source to drain. But what we want to now find is what is that distribution in K space. If you find what is the distribution in K space now you see there's looks rather complicated. You have certain length of the channel, you have width. What do you mean distribution in K space? Where? At what point in X? Because things are changing as you go along X now, right? In the flat band condition, everything was the same. This, situation were similar, but now things have changed. Right? The way to look at it now is, look, I have a Fermi level of source. So this, source is still trying to inject carriers to go to the left, but you can see immediately that it has a much higher barrier to get over this. The barrier height has suddenly increased by how much? By this much, by the applied voltage. Right? The barrier has suddenly increased by quite a bit. Right? Therefore, what's going to happen in this picture is maybe you can help me. What's going to happen in this picture? So yeah, it'll change, right? So clearly, if I ask the question that, so it can change, but it depends on where you are in the channel. That's the important point. It depends on where you are in the channel. If you're sitting here, then that's still like that, right? If you're sitting here, the right going part is like that. I don't know what is the left going part now, right? But there's one point which is of very great interest, and that point happens to be what's called the source injection point. You see the bands, because they bend, like this, it goes from a positive slope to a negative slope. So at some point, there is zero slope. At some point. And that's called the top of the barrier, So this is top of the barrier. That's one point where the slope of the band diagram is zero. What does that mean? At that point, if you think of it classically, there is no electric field at that point, because electric field is the derivative of the potential, and there is no derivative. It's flat, right, at the top, right? There's no electric field at that point. So at that point, and that plane is called the source injection point plane. And what we're going to do is ask the question: what are the carrier densities at that injection point? And that's a unique plane here. Right? You can kind of see that has to be one of the unique ones, because every other point which has a flat band is kind of in region which are in equilibrium with different things, which is not capturing the whole picture, but that point is capturing picture of what's happening from both source injection and drain injection. Okay. So at that point, clearly what has happened is because of the, let me sketch this picture on the side now. Kx and Ky. And now I'm going to just draw circles and forget about the discreteness or the grid points of that. What we're saying is, look, because the drain potential or the quasi-formula, the formula of the drain is so much lower, the amount of carriers that that's going to the left has suddenly gone down exponentially. Does that make sense? It's gone down exponentially because the barrier height is increased. To picturize that, we are going to draw, it's still injecting some, because there's always a tail. Remember, there's still, the tail is certainly, there's a much smaller tail, but there is a tail, right? That gets injected. So maybe what has happened is this whole, big circle going to the left has suddenly shrunk to a very small circle here. Right? That's the one that's injected to the drain. But now, what's going on with the carriers injected from the source. And this is kind of the tricky part, which one might first say that it remains exactly the same. That's the first thought, right? Because the barrier height has not changed. Right? So it's exactly the same. But the correct answer is it's going to increase. It's going to increase, and that is the heart of the FET. That's the most important thing about the FET. In a well-designed transistor, the carrier density at that point, which is the source injection point, is not controlled by the source or the drain. Okay, so this is the heart of a transistor, a field of a transistor. The carrier density that is responsible for the most of the transport in the channel at this source injection point is not controlled. It's controlled neither by the source nor by the drain. It's only controlled by the gate. The gate has complete control over how much carriers are there at the source injection point. Right? So what does that mean? It means if the gate says this is your carrier density, no matter how much source or drain voltage I apply, this is always the carrier density at that point. So it is in complete control. This happens only in a very well-designed transistor. If you don't have it, it's not a good transistor. No? Because this is the heart of gain. If the gate cannot control how much charge is flowing between source and drain, then it's as good as you have 3 resistors connected to each other. There is no gain in 3 resistors. This is the heart of the problem. So gate completely controls. It dictates what is the total area, because the total area is the carrier density. And source and drain only control how are they distributed in K space. That's all the control, right? Does that make sense? This is actually a very important point. If the gate cannot control how much charge is in the channel in the FET, then it's not really a FET. This is many times people will show these devices where the claim is FET, but you can ask what is how much. What we'll see is you get all these short channel and dribble and all that sort of thing. That's all because the gate has lost control over the channel. So, with that thought in mind, if this area has shrunk, clearly you can see the right side has to increase to keep the area the same at the same gate voltage. Does that make sense? I mean, the area must be the same. Right? Or in other words, the carrier density is the same, and therefore, let me just sketch it, maybe a little bigger circle on the right, something like that. So more carriers are going to the right. And the initial situation was, this dashed line here. And now you have a redistribution of occupation function in the K space. It's just a redistribution. Right? Does that make sense? I mean, at least what we are trying to claim is the gate is in complete control of the charge at the source injection point. And the moment you do that, now we are ready to write the answer down of how much current is going to flow and all that stuff. Because the current was actually the same. You see, all these carriers moving to the right had a certain amount of current flowing to the right, and that current was, let's say, J0, flowing to the right. And that was exactly equal to the current that was flowing to the left. Okay? So that's also J0, and they were, this thing was going to the left, and that thing was going to the right, and they canceled each other out exactly. Because for every state here that's going with the velocity that way, you can find an exact opposite state here that's going exactly opposite direction. They cancel out exactly. Right? The velocity is exactly cancel out, and therefore the net current was 0. But the moment I do that, you can see now you have a big right going, like a ring of states, and that's going to give you a net current. So, yeah.
So down the channel, this will start moving.
Yes, very good point. So we are kind of making not an assumption, but actually it's a very clever way of getting around the problem, and we'll see that we'll do that again when we do the PN junction, hopefully a little bit today and then in the next class. The beauty of the problem is the current is always continuous. No matter where you are, the current is the same, right? Because if there's 1 milliamp per micron going in, it's 1 milliamp per micron coming out. It's always the same, and therefore you can choose any plane to calculate the current. And then what we're choosing is this plane. But once we go here, the distribution will be very different. It won't be like this. And let me just show you a numerical simulation of that. This is from a very nice paper also from, here's some nice pictures. So what I was just trying to claim. So this is now in 2-dimensional space, kx, ky. When I'm drawing circles, you realize that Fermi-Dirac distribution is 1 when it's very low argument, and then it kind of kind of goes through a step, and then it has a tail and all that, right? So when we say, so the surfaces are not as sharp, but what we are getting is an exact expression now. And here's for example out in the source, and we are looking at the right half going carrier. And at the source injection point, you see, pretty much looks like all carriers at a reasonably large drain voltage, all carriers moving to the right. It's a two-dimensional case space now. And if you go a little bit to the right, you have essentially what happened is you have this injected beam of carriers. Okay, you have this injected beam of carriers that have, quite a bit here, and then there's a little tail that's going down. Right, so this beam is moving. Right? And as it moves, the band is moving down. So but it's moving at the same energy. It's like you're sitting on a hill and you're shooting, bullets, but actually its kinetic energy in this picture is increasing. So it's getting faster. The electrons are moving faster as they go along because the kinetic energy is increasing, and that's what is showing that the velocity is getting faster. Does that make sense? I mean, it's the same thing. And then when you reach the drain, you have still those very fast moving electrons, but you also have this whole sea of other left and right going carriers. So they kind of merge, and then it dumps all the heat up there. And so when people measure these devices, the drain is hotter. You can measure it. Temperature is hotter because the electron just dumped all its energy into the drain contact, not in the channel anymore. If you have a very long channel, then you have Joule heating and heat. Here, there's no chance for the electron to relax. It just it shoots, and then it lands in the drain, and all the heat goes there. Right? There's still dissipation. Ballistic, no scattering, is no scattering in the channel, but there is a lot of scattering in the drain. Once it reaches there, it reaches equilibrium with it. So that's the picture now, and I think you can look up those slides. There are quite a few more. When you apply different drain voltages is 0. You have symmetric distribution in case space. You apply a little 50 millivolt drain voltage. You can see there's a right going half that has gone up now. Right? Left going half has gone down. But if you integrate the area, it's still the same because the carrier density is not controlled by the drain or source, it's by the gate. So that's the key difference, and that is the heart of gain of the device, and then all the things that are good about the transistor, and so on. You can kind of see all that stuff now. Okay, so now what I'll do is again we're a little time crunch for me, but what I'll do is I will write down the expression for the current. What we did was we wrote down an expression for the carrier density. Where is that? Here's the carrier density, right going semicircle, left going semicircle. Right going semicircle is here. If you use colors, this is because of the source. I think you can see the pictures and connect it to the math here. This is all the, we are summing. This is kind of the area, the natural log of this times that is the area here of the right one. That's the area. So because that's what we did. We integrated it. We summed over all states. And similarly, the area of the left going one is here. This times, when I'm saying a natural log of that, and when you add natural logs, the arguments just multiply, right? So that's what happens here. Now for the current, it kind of almost done now. Current is exactly the same expression as carrier density, except that there is a velocity sitting here. That's all there is. There's the velocity sitting here. Right? You're summing all states. You're summing the group velocities of all states. That's the current expression. The expression for the current. And so when I write that, current is. Let me just write that once, and then I will not derive the whole thing, but I'll leave it to you. So we're sum again to the right of Fermi kx, ky. Actually, let's write it. Group velocity. And if it's moving to the right, we know now that it has to be in equilibrium with the Fermi level of the source, right? Plus, again, there is something here which is going to the left, which is, I think you can write that down. Right? So there's Fermi level of the drain and such things. But the more important point here is that there is you're taking kind of first moment of this now. There is a group velocity sitting in front, right? So the group velocity we just wrote is actually a very simple relation. It's just that. That's the group velocity. Right? And you can see again that in this picture, from this picture, what we are interested in, because you're applying a voltage across this, what I'm really interested in is the current flowing in that direction, the net current going from left to right. I'm really not that interested in how much current is going that way or that way. So what velocity should I choose? It's the component of the current or the velocity that's going to the right. So I should just choose kx or take a projection along the x direction, right? Because these are vectors. These states are moving. This is a vector that moves in that direction. I take its v, magnitude times cosine theta, right? That's what I should take. And then sum all of them up. Right? So instead of summing, the group velocity, what you do is, let me rewrite this. We just do the right half and then, make the connection now. So let me just write it now in terms of a sum. Again, dkx, dky, always, 2 pi over L, 2 pi over width, we're summing over modes. And the x-directed velocity is h bar times kx over m star. Right? H bar times kx over m star of the conduction band. Right? This times our old Fermi-Dirac distribution, exactly the same thing here, right? With the source function for the right going carrier. So these are the carriers going to the right. And this is, again, 1 over 1 plus e to the power. I'll write it in the units we used earlier, m star c kt minus eta sub source. So that's to the right, and then you have something to the left. Now again, you do kx, ky, circular coordinates, but now kx is actually k cosine theta, right? So you also have to take care of this theta integral, d theta times cosine theta, and cosine theta integrates to exactly 2 if you integrate over half circle. Yeah? Only half circle. If you do full circle, you get a 0, right? So, but if you do only half circle, you get a 2, and that sort of thing. Okay. But once you do that, all that stuff, let me write down what you're going to get. Again, you can see it's really not going to be too different from this, but this integral will have a form of, you can now substitute this as, energy over kt and that sort of thing. You'll have an integral of this form, square root of energy over 1 plus e to the power, minus eta s over. It will look something like this. So this is a Fermi-Dirac integral not of order 0, but of order half, because there's a power half in the numerator. So it's a half-order Fermi-Dirac integral. And half-order Fermi-Dirac integral is not exactly doable, meaning you don't have a closed form, analytical form. So we just write it in that way, f of half. Just like we wrote f of 0 here, we wrote f of half. So when that is said and done, what you get is that the current will be J naught times f of half of eta source minus f of half of eta drain. So that will be the current in the transistor. Again, these are just closed form. This is an expression for this integral. There's really nothing more fancy than that. What is that J naught? The J naught will be a product of 3 things. There is Q. If you remember, we had derived something called the quantum carrier density times some sort of an injection velocity. I think there's something, people go back and forth between. But, if you see the carrier density, it has all these things. Density states, KT, it will also have it there. And let me write that down, okay, in a little more detail. So the net current, I'm running out of space here and time. So, okay, let me rewrite that. So the net current in the ballistic FET will be Q times n quantum, which we had derived in the last class, which looks like, the quantum capacitance, which is Q squared times the density of states, times the thermal velocity, thermal voltage over Q squared. So n quantum was CQ times the thermal voltage. Okay, Q squared voltage times, these are things you can actually just write down from evaluating that integral. All these factors just come out of the integral. So these are natural quantities. This is what we call as n quantum. This is what we're calling as some sort of an injection velocity. Charge times density times velocity is current. And the factor that depends on all the voltages are sitting here. Eta source minus f half of eta drain. So this is all the controls. You have two controls in a transistor, the drain voltage and the gate voltage. Everything else is a response to it. Okay? And we are calculating the response, and all of them are sitting here, source and drain. They're all sitting there. What's the control? Okay? So let me make sure I have written this right. Okay, CQ, V thermal. Oh, V thermal over Q. Okay, so there's a Q here, which is what I missed. Okay, so there's a Q. Yeah. Okay. So this is a whole expression for the ballistic current. And now the question really is, you give me an expression, but now how do I actually evaluate it? Is you need to know these two quantities, right? What are these two quantities? Coming back again, eta sub s is Fermi level of source minus the conduction band edge by kT. Eta sub drain is Fermi level of the drain minus conduction band edge over kT. Right? This is in pictures. It's this and it is this. So clearly, inside these two quantities is buried all the effect of the drain and the gate voltage, right? It's pretty clear, right? So all the effect has to be in there because there's nothing sitting out in front. Right? This is kind of equivalently what you might call as your, Schottky diode, the J naught current, and this is exactly what your, yeah. So this is a coefficient, and it's kind of equal and opposite in both directions. That's the current, and you're breaking that symmetry. If your source and drain are exactly at the same potential, this and this are the same, you see go to zero, right? And then this is the part which is still flowing. It's just equal and opposite. That's what it means. And now you see that if I take so that's eta sub s and that's eta sub d. Okay. What's the difference, right? So eta sub s minus eta sub d. What's that? So, this minus that, right? That's right, and that happens to be Q times the drain voltage, right? Source formula minus YKT, right? Or KT by Q happens to be just the thermal voltage, so that's that, right? And so instead of writing that I have two unknowns, you see that eta sub drain is just eta sub source minus this quantity. Let's just call this. I know. I mean, I apply a certain drain voltage. I know what that voltage is. So that's completely different. Let's just write it as small v sub d. I mean, that's the that quantity. We'll label it as small v sub d. You can call it VDS, but I think that's the label that Natori uses. So I just write it like that. Right? So really, instead of writing it in terms of two unknowns, what you have is really one unknown. And that is okay. So minus v sub d. Okay. And the unknown is just what is this eta sub s? If you know that, you have the answer at your fingertips. But basically, it has all the answers in it. And we'll see now that to find that eta sub s, you need to know all voltages, drain and you need to know drain and gate voltages without it. And there's an equation that gives you that. And that's that. Once you get that equation, the problem is completely solved. You just plot it and all that. Now, how do you find eta sub s? And the answer to that goes back, again, to the heart of the transistor. The heart of the transistor is the carrier density is controlled by the gate in the source injection point. And that's the heart of the problem. So you go back to here. Right? It makes sense? I mean, this is where we come back to. And realize that eta sub drain is really related to eta sub source minus VD. Right? This equation is still true. Now, it just happens if VD is 0, then you have equal terms and you have equal half circles. But when VD is not 0, you get this situation. But the carrier density is still controlled by the gate and it has not changed. Does that make sense? I mean, it has remained the same. And it might look like a rather complicated equation to solve now because we're saying, look, you know everything here, you know everything in this problem except in some sense. So in other words, how does this depend on drain and gate voltages? clearly the drain voltage dependence is sitting here, right? And the gate voltage dependence is sitting there. Right? So you need to solve this equation to get what is eta sub s as a function of gate voltage and drain voltage. Right? And this equation might look very formidable, right? I mean, it looks, oh, yeah, how do you solve this equation? It looks formidable. But actually, you'd be amazed, but this also has a closed form analytical solution. And as I claimed earlier, many times in semiconductor physics, you get sometimes stumped, oh, this is an unsolvable equation. But most of the action is happening in exponential space. This is actually, believe it or not, a quadratic equation. It's in disguise, it's disguised as another equation. So if you just strip away its details, what you realize is this equation. I have already written that down. Maybe you can already see it, maybe not. So you can again retransform all this stuff. Take the 2 here, and 2. And you remember, we can absorb this d naught and kTs and all that into our quantum capacitance, quantum carrier density. So we just write it like that. Right? And then you exponentiate both sides again. Okay, you exponentiate and all that. So so this becomes, again, I mean, I'm doing all the details again. Ln, natural log of e to the power this whole thing, right? And now you can see, you can start solving. So you take away the natural logs now, and you get 1 plus e to the power eta s. 1 plus e to the power. So this is not n, carrier density, but it's this eta, which we are looking at, eta sub s minus vd is equal to e to the power 2 over nqp. Right? And remember, we are after this quantity. And so you can write now e to the power eta s as x. And you can see now it is 1 plus x. 1 plus x times some other term vd, right? So you get a x. Does it make sense? So I write it as x, and you get an equation that looks like a x squared plus bx plus c equal to 0. That's what you're going to get, right? And then you take log of that x, and then you get eta sub s, which is so it has a little bit of a long expression, like which, but it has all these quantities that maybe, yeah. Sorry for not showing up clearly, but okay, that's how it looks. So eta sub s is natural log of something, and this is something you can plug in and plot it. So with this, what's sitting in there is eta sub s, which is the source degeneracy function level, depends on the drain voltage as v sub d, which we defined. Where did we define it? It's your drain voltage over kT, right? So VDS over thermal voltage. So once you know you have applied 0.2 volts on the drain, you know what that is, right? So VD is a number. So it depends on that. There's a square. This is just a solution of that quadratic equation we just wrote. This is a solution. And once you define what is the gate voltage, the whole game now is go back here, solve this first, find out what is NS versus VD. First find that out. Right? And this has nothing to do with the MOSFET at all, actually. It is just a MOS capacitor, right? Metal insulator capacitor, right? Once you find that out, you have a tabulated, or you have this value already for you, NS to the power VG. And then you apply drain voltage, and you just evaluate this term, eta sub s. And once you know eta sub s, plug in here, got your current. Does it make sense? I mean, that's the whole story of the ballistic MOSFET. And here's an example of some plots. Once you make the plot, okay, I already showed that one to you. So this is what I'm doing here. By the way, this file is posted, so you can actually look at it. I'm defining all these quantities: barrier capacitance, quantum capacitance, thermal voltage, V sub D, which is defined that VDS over thermal voltage. And here's my current. I'm defining it as this is the coefficient, and then I'm solving for NS as a function of VG, carrier density as a function of gate voltage, and then here's my carrier density as a function of gate voltage. I've already showed you that. And then I define my Fermi-Dirac integral of half order. You see, this is something we did today, square root of something over 1 plus exponential. Define all that stuff. And then write down your ballistic current is whatever this J naught coefficient times Fermi of the source minus Fermi of the drain, Fermi integral of the drain. Right? And here's the current. So drain current as a function of gate voltage, drain current in milliamp per micron. Those are the units. So you can check the units here. The units preferred in semiconductor FETs is milliamp per micrometer. How many milliamp per micron width of the device? If you have a wider device, it's more current. Right? So you can see the picture here as a function of the gate voltage. So what are we doing here? We're just plotting this function now as a function of gate voltage at a fixed drain voltage. At a fixed drain voltage. And at a fixed drain voltage, the current is very low when the VGS minus VT is very, up to the left. And you see this picture is a complete copy of the carrier density picture, right? It's a complete copy of the carrier density picture. It's just, going down at 60 millivolt per decade, close to that, and then once you turn on, it kind of starts, saturating in some sense. Right? But it's not a saturation. Here it becomes polynomial, and what you can show is when VDS is very large, you get Fermi-Dirac integral of a very large negative quantity, so you can forget this one. Only this one survives. And when that survives, you will get that the current becomes proportional to your gate voltage to the power, I think, 3/2. That's what it's going to become, proportional to gate voltage to about 3/2. From here, you can just do some algebra and find out this is how it's going to be. And historically, it's a very interesting problem because, as a precursor to the transistor, what came before transistor? What did people use for switching and amplification? Vacuum tubes, right? In a vacuum tube, people had an emitter and they had a grid. And a collector, okay, so a collector plate. So electrons would kind of go through the grid, and this will control whether electrons go through or not, right? And in a vacuum tube, they had kind of the grid voltage, current dependence was the same. And it's very amazing because it turns out that in a vacuum tube, you really have a ballistic situation. It's vacuum, there's nothing to scatter, right? I mean, it goes back to the same situation. In a ballistic transistor, the current, when you plot it in the linear scale out here, it goes as similar expression as vacuum tube. We have taken away all the atoms. If there's no scattering, then really the atoms are not playing a role anymore. So it goes back there. Right? So that's a function of the gate voltage. Very sharp off, and when you turn on, it kind of doesn't. It slows down and goes something like that. And the other very important part of the transistor is when you plot the drain current now as a function of the drain voltage. Right? So now we are changing VDS. So for a fixed gate voltage, when VGS, gate voltage is sitting maybe over here, which is kind of on with a large enough gate voltage, then you get this blue curve on the top. So look at the numbers. Numbers of the order of 1 milliamp per micron. And that's today's MOSFETs. The best transistors today are kind of around there. 1 milliamp per micron. 2 depends. I mean, for example, in gallium nitride, people have reached almost 4 milliamp per micron. I mean, this is with very short gate lengths and that sort of thing. But very importantly, the current increases initially. If you were just looking at this part on the left, it looks like a resistor, right? IV curve. It's a resistor. That part of the transistor, as far as gain and switching and amplification goes, is completely useless. It's not very useful. It has some other uses, but not in a amplification and gain picture. All that business happens here. The current must saturate, otherwise there's a big problem for you. And interestingly, people, before they thought of transistor as a quantum mechanical object, they thought, once you put in all the quantum mechanics, there'll be all sorts of interference and this, that, and we'll get, oscillations in voltage and all that. None of that happened. It's just a straight on, saturation. And in a long channel transistor, if you have a transistor that is, 100 micron channel length compared to 10 nanometers, it looks exactly similar. It's very interesting. I mean, the quantum picture also gives you the same thing. Exactly the same thing. It saturates. Now, you might ask, why is it saturating? And you can see the picture from there very clearly. And then that's kind of a nice point to realize that once your drain voltage is large enough, what is happening in K space, right? So the electrons are injected from the source and the drain. But once the drain voltage is large enough, this thing shrinks and shrinks, and then it completely goes away, right? Then all the electrons that are in the source injection point are moving, have come from the source, and then their density is not changing anymore, right? So they're all moving to the right, and they're already carrying. You have already summed up the velocities, and the current is not changing anymore. Does that make sense? I mean, so that's the reason in this picture. That's the reason why the current is saturating, because the number of electrons is completely controlled by the gate. And once you fill this, there's nothing else to do. You can apply more drain voltage, nothing else is happening. So it just gets locked here in some sense. It's a simple picture, but it works pretty well. There are obviously complications to it, meaning if you apply a very large drain voltage, there'll be breakdown and tunneling and that sort of other things. And those things have been turned around to make devices of the future. But in the devices of today, this seems to explain this whole business here. Okay, so the other very interesting fact about the ballistic FET is when people started making these transistors very small, they noticed that in this region. Okay, I'm now kind of out of time, so clearly no p-n junctions today. But let me make that little connection I mentioned to a classical, picture of a transistor. So is that clear? Any questions about the ballistic FET? I'm just going to actually now make a connection to what happens if you introduce scattering, and then that part is relatively easy to figure out. But any questions at this point? It's clear. So what I'm saying is you have a closed form picture for the entire transistor operation with this expression and some of these carrier density expressions, and under certain situations, if your drain voltage is very large, you have simplifications, and if you are in the on state, you have other simplifications, that sort of thing. Okay? But if you make the channel very long, such that if you are scattering, you introduce a lot of scattering, in the channel. So it goes, scatters and relaxes, and scatters and relaxes, and that sort of thing. That was the original theory of this transistor, which was initially conceived by. The theory was put together by William Shockley and people at that time, and Pao and C.T. Sa and others. And that picture was, I can write it down in like 2 or 3 lines, and we have maybe a couple of minutes left, so let's just finish that right now. Okay? The old picture of the transistor looks like this. Okay? So let's go back. I've already drawn that. It's actually a very nice picture too, but it's completely classical. You'll see now. Right? So the transistor, again, we are trying to find what's the current, right, at any point. Right? And what Shockley says that, look, I'm going to go a point here, and this is my length L, right? I'm going to this is my x-axis here. I'm going to ask the question, what is the carrier density at that point x? Right? What is n of x? Sheet carrier density. What's n of x? Right? Well, what is n of x? Classically, you see you have a parallel plate capacitor here. Forget about all quantum capacitance. Just forget about all that stuff. Classically, you have a parallel plate capacitor. Right? This end of the capacitor is at a gate voltage minus VT. We can scale that out, VGS minus VT. This end is at an undetermined voltage. Right? Inside the channel, it's undetermined. What is the voltage? It is V of x. We don't know. But I do know that if I reach here, I am at 0. And if I reach there, I'm at VDS. I know that. So I know the 2 boundary conditions. Right? And that's enough. You can actually solve the entire problem with this, and that's what Shockley did. So he says that, look, the current at any point in the transistor, J as a function of x, current density per unit width as a function of x, is equal to electron charge, if you're moving electrons, times the electron density times the electron velocity. That's straightforward, right? Not much to say about that, right? Correct. And this is also true quantum mechanically, but the beauty of it is it really doesn't depend on x. The current is continuous, right? If certain current is flowing here, it's also flowing there, right? This is a very important relation now. So and what he says that the current, the electron density is gate capacitance times VGS minus VT, because if you don't apply a certain threshold voltage, you can't put carriers in a semiconductor. That people knew even then. In a metal, you get at 0 volt, but in a semiconductor, there's a threshold voltage. VGS minus VT minus that channel potential at that point x, local potential. Right? Now this C times V gives you coulombs per centimeter square, so you divide by Q, and if this Q just goes away. Right? Times velocity, and this is where we make a connection to what we had talked about earlier. Velocity is mobility times electric field. Right? Mobility has this scattering concept now, right? But what is electric field? Electric field is dV over dx, right? Negative of that. I'm switching I'm forgetting what signs and all that right now. Spatial derivative of potential is the electric field, right? So this is mobility times the electric field is the velocity. Remember we talked about drift, diffusion, mobility times speed. So you substitute that, you get mu and dv over dx. Okay. Now if you want to really find the total current, I, flowing into the drain, it is the current per unit width times the width, right? So let's put that width here, W. Okay. I just put the width back, right? Total current. Is that clear what we did? And this is it. I mean, once you look at this, what Shockley realized, well, since the current is continuous, let me bring that x over to the left. And you see now I've decoupled the two. And I'm going to just integrate both sides from x is equal to 0, which is my source end, right? From here to there. So integrate it from source to drain. So at x is equal to 0 and x is equal to, L. That's the length of the channel, right? And at x is equal to 0, my potential is the source potential is 0, right? And x is equal to L, my V of x is VDS. Makes sense, right? Do you see what I mean? This is actually, and the beauty of this is the simplest integral, right? You just get ID times L, right? You take L, take it to the right side, and you get mu gate capacitance times W over L. If you have done any classical semiconductor physics, this W by L appears again and again, width over L. If you've done any CMOS design, it appears very often. Okay? Times, you see the integral here is trivial too. VGS minus VT is a constant, so you get VGS minus VT times the drain voltage, right? It just gets multiplied here, minus VDS square by 2. Right? So that's your current. That's Shockley's theory of a long channel transistor. And you see what appears here, which does not appear in the ballistic transistor, is L and mu. These things don't appear in the ballistic transistor, right? L is the channel length, and mobility depends on scattering and all that stuff. And classically, the transistor physics FET physics has always focused on this sort of picture. And the idea was always to improve the current, to make a transistor better and better. And to do that, you always look for high mobility materials. You look for high gate capacitance, so you make the capacitance thinner and thinner and thinner, and make high Ks and that sort of thing. So that's the picture. And if you plot this, there are some other things. I mean, it doesn't explain the off state. For that, people have used surface potentials and other things like that. But it's kind of thing. So this is a classical picture of a transistor. That's the quantum picture of the transistor. And interestingly, when you plot it, there are actually a couple of things which I'm not mentioning as far as saturation. There's the surface potential, but they will look same if you plot them in the end. So this picture kind of covers the triode region, or this part of the curve pretty well. But people were actually very worried when they actually were making transistors smaller and smaller, and they were using this expression. Then you can do dID over dVd and all that, and you can pull out what is my mu, right? We measure experimentally, and pull out what is mu. People started observing when the transistor got smaller and smaller, people thought that, well, there'll be less scattering, so my effective mobility should be higher, but actually they saw the number they were getting was smaller and smaller. And the reason for that is really nothing special other than the model doesn't work anymore. I mean, you have to go there, right? And then so they kind of baffled people, why is the mobility getting smaller? But really it was nothing to do with the mobility, because it just didn't, that expression didn't work anymore. And so, okay, so let's actually end it today. Again, we didn't get time to do p-n junction, but at least we finished the FET. And what I've told you, as I mentioned, is the more modern picture, but to do good justice, one should have both the classical and modern picture. I can suggest you to read a few books and articles as well. And the next class will focus on the p-n junction and try to do as much of the bipolar as possible in the next class. Thank you.